Hello everyone, my name is Sentongo Joshua and I'll be presenting to you the Knowledge Distilled large acoustic models. So let's get started. So a brief background. Systems today, the ones that do recommendations of music, they lack emotional cultural relevance. The system we are creating here is supposed to bridge the gap between the user and the music that they listen to. It is supposed to personalize how they engage with music. This is a brief flow of what we did. We obtained a data set, captured the acoustic tonal features. That was for the basic models that we began with. Then we align those features with the emotional annotations. And that is for the first stage of our system. The goal here is to create a system that can classify the emotion that a song contains, the predominant emotion. So these are some of the related works. I'll go through the most important ones that uh, played a very important role in our system development. The, the one that was made by Janaki, the DIM dataset, that's what he used. Then we have the music induced emotion flow. It also used the DIM dataset. Uh, they deployed the efficient net model, and that is their mean square error that they got, which is small. Uh, the problem statement here is that since people relate to music emotionally, and systems today are not doing a very good job at addressing that need, our system is coming in to solve these domain problems. First, there is a limited understanding of music in an emotional manner. We shall create a system that is able to detect and classify the emotional makeup of a song. Next is models today are general, so they are not focused on the context of different users from different countries. And the fact that even the data available, music data, is not annotated enough, especially for non-Western music, that even makes training harder. Then larger models that are able to do this kind of analysis, yes, they can do it, but the problem, they are resource intensive systems. They consume a lot of memory and uh, processing power. So the system we are creating is going to be one that is distilled. Therefore, it is smaller and yet keeps the accuracy of the parent model from which it came. Next is the latency, the amount of time taken for a user to receive a report after uploading uh, their song or audio file for analysis. Now, these are the objectives of our research, and we have managed to accomplish uh, them. So, first is to quantify the musical features and relate them to the audio features, to the emotions in a song. Then we also synthesized more data in addition to the limited amount of data that came in the data set. And we did that using our gun. So to create a large vision model, which we did, yes. And also to distill it so that it is small enough to be deployed on an end system. So we researched about the Google Vision Transformer, which is a good model that we pre-trained on the audio files we had that had been turned into spectrograms because it is a vision model. Next was the AST from MIT, also a transformer that works with audio spectrograms. Then we created a GAN system that synthesizes audio spectrograms to add onto the small data set that we had so that we can have a large training set. Then we built a feature importance framework to correlate our, to determine the features an audio file that correlates to the best emotions. So this is the methodology and architecture of our system. Here we have the very first thing is a gun, which takes in training data, and then random noise goes into the generator, and then the generator outputs fake samples of spectrograms plus the real samples that come from the real data set. The discriminator's role here is to identify the fake from the original, the fake from the real, and it is more like a mini max game whereby one tries to uh, win the game. So the generator has to become good at faking such that the discriminator is unable to tell apart the real from the fake, but then the discriminator has to become so good at identifying the fake or the counterfeit. So this process is a cycle because the output still comes back, and the entire system becomes better at producing data that is close to the real. Then that data is pushed into our model. In this case, the audio spectrogram transformer, which breaks each spectrogram into 16 patches, and then those patches are passed through a linear projection, which turns them into a one-dimensional array that is worked upon by the further layers of the transformer until we have a head that points to the emotional label, as well as the values and arousal values that are output for the user. Now, this is the architecture of the distillation process. This is an overview. The data that is trained on the teacher model, is, the teacher model's role here is now to transfer knowledge to the student. How? By getting predictions from the student and then providing feedback to the student, letting it know of what patterns to pay attention to and how different features of music relate to each other. So the student learns from the teacher, and yet at the same time, it becomes smaller in size and hence can be deployed on a smaller system. So for the gun, as I said, it is a min-max challenge whereby has to uh, the discriminator has to minimize, and then the discriminator actually has to maximize, and the generator has to minimize its loss. That means that the discriminator has to be able to generate data that is close to real, and the generator has to become so good at detecting the fake data. So in the end, we get samples, size samples that are close to the original. Then next is the transformer. So each spectrogram here has a height and a width represented by H and W. The height is 224. The width is also 224. Plus each spectrogram has 3 channels, and that is the RGB. So in total, each spectrogram is a 3-dimensional entity before it is processed any further. But the transformer won't work on a spectrogram in its raw form. So we break up a spectrogram into 16 by 16 patches. If you do the math, that gives us the number of patches to be 196. And each patch has 3 dimensions still, because we have not yet passed it through the linear projector. So it has 16 by 16 by 3, the vector of 16 by 16 by 3. So that is a total of 768 dimensions per patch. But how many patches are there? There are 196. So we have X that represents our patch embeddings. So each patch is a vector that is made up of 196 by 786 vector. The vector that is represented by that 196 by 768. So we get that patch embedding, which is just now a matrix that is a stack of each patch, which is made up of 768 values, and we stack all of those 196 patches to get this matrix, which is a 2D matrix. Now we pass that into the linear projector that transforms it into a 1-dimensional representation of the entire spectrogram, and that is what the transformer is going to analyze or train on in the further processes of transforming it. Now, here we have a multi-head self-attention. Now, this right here is able to relate the patterns learned from one patch to the other patches. So each patch has that it relates more to certain patches more than others. So that is the importance of this multi-head self-attention. So this is a video system, and we have audio coming in from the user in form of audio files, and then they are turned into spectrograms, and our system will work with the spectrograms. It analyzes them and then outputs a report for the user. We also plan to connect to third-party systems such as Spotify and YouTube Music or Apple Music, so that the system can create a database of the emotional analysis of the songs, in such that if a user needs the analysis of a certain song, it doesn't have to do it all the way from scratch, but can return a value stored in the database. So the description of our data set is that it's from the University of Geneva. Yes. And you look at this heat map over here, the maroons or the reds, depending on how you see color, represent high correlation coefficient, and the blues represent negative correlation coefficient. So we picked the reds because of their high correlation coefficient, meaning that the way they relate to each other is useful to us in such a way that can use them to determine what emotional characteristics the song possesses, unlike their cousins, the ones that are negatively correlated. So we just shows that we generated more spectrograms in addition to the few that we obtained from the audio files. And now you see how the synthetic and real spectrograms relate to each other. They were able to come close enough to the real, so the GAN did a great job. This is a comparison of the models that we came up with: the reach, the support vector, the CRNN. Those were the basic models we began with that used the features, the text-based features. Next, we changed path to pay attention to the transformers, which used visuals of the spectrograms instead to analyze patterns and the features in audio. These are the results of the Google VIT model, one of the best that we got, and you can see how well it did by how close the training and the validation graphs come close to each other. The expected results are in blue, and then the predicted ones are the ones in maroon. And if you look closely, you can see a pattern that the model was able to pick up, and the predicted and the brown truths are actually close enough to the center. Now, we are selecting the Google VIT model, the base model that we pre-trained on our audio spectrograms, because it had the highest concordance coefficient, correlation coefficient. It did a very good job in predicting, and we shall deploy this with the back end on render, and then the front end will be on Vercel, and the two shall communicate via fast APIs. So we shall have our GitHub. This diagram shows that our GitHub has the repo, and then the repo is the one that is connected to render and Vercel, and then Grafana will be for monitoring. So the users will connect to the system, the front end, via their browsers onto Vercel, and then Vercel will talk to render to send it the audio files, and then receive back the analysis later afterwards. This is a picture of our screens for the system. So some limitations of the system is that distilled models suffer from a little bit of inaccuracy, because during that transfer of knowledge, there are some patterns that are lost. So that is one of the major limitations that I can talk about, among others. So and conclude and make some acknowledgements to the University of Geneva for providing us with the DIM dataset, and also Dr. James Russell, who is a prominent psychologist, for coming up with the circumplex model, the valence arousal model that we used in our system. So I would like to end there and say thank you for listening.